I would like to thank, like most of us, Grégoire for doing a great job in this workshop. Really very involved and very successful workshop. So I understood from the previous talk that I have basically illimited time. No, so I will go very slowly. No, I'm kidding. I'm trying to fit in 1 hour. So what I would like to tell you is how one can actually study simple frustrated quantum Hamiltonian with iPEPS, and the type of state we are looking at are topological chiral spin liquids, and I will focus on the square lattice here. And these states actually are very exotic state, but very nice because they are the analogs of the fractional quantum state in the plane. So this is what we like to see being realized in frustrated magnets. So the outline is the following. So I will start with some motivation. Then I will explain briefly the type of ansatz we are using, which is this projected entangled pair states, and how we handle these things with the iPEPS method, which is a method that actually works directly in the thermodynamic limit. There is no finite side effect, so which is quite nice. And then I will go to the real main part of the talk, which is investigation of some simple frustrated Heisenberg models, which have some degree of fine-tuning still. And they will be completely spin symmetric, SU2 symmetric, spin 1/2 and spin 1 models. And I will try to convince you that these models indeed host abelian and non-abelian chiral spin liquids. So in the previous talk, I think Alex introduced this, and maybe Cécile also, the Camille-Laughlin state. So this is really the paradigmatic chiral spin liquid that we understand very well. So the construction was already introduced a long time ago. The idea is to take the bosonic fractional quantum state, so the nu equal 1/2 fitting nu equal 1/2, and basically just to localize it on the lattice. Okay, so there's a very simple prescription that if you have a particle, you have a spin up. If you don't have a particle on the sides, basically it's like you have a spin down. And this state turned out to be completely SU2 symmetric. It's a singlet. And it describes an abelian chiral spin liquid. So there are some issues, and one of these issues is whether there are simple parent local Hamiltonians. We would like to have a local Hamiltonian because this is what we have in materials that actually host such states. And whether these states, another issue is whether these states can be described in the tensor network framework, which is the technique I'm using and which seems to be very powerful. And so it would be nice that we can generically describe such state in this technique. So the type of state we are looking at are actually very, yes, Carlo? No, okay.
Is it simple to show by the Laughlin wave function is a singlet?
Federico just asked me the question. I think he found a paper by Gervin from well.
They claim this, but I'm not.
Yeah, I think it's not so straightforward.
Well, it's not so.
Yeah.
It's not extremely hard. So I think you can look up the reference. So there's a 3-line argument.
And it's only for a very large complet or something. You need some thermodynamic limit now.
Yeah.
In the finite system, it's not really.
Yeah. Yes. Yeah. Okay. So the reference is a paper from 1993, I think, by Gervin. They do the. So the type of state we are looking at is are actually very exotic in the sense that they don't, follow the usual Ginzburg-Landau paradigm, in the sense that there is no order parameter, but they do exhibit long-range order. And the type of order they exhibit is topological order. And you can define topological order in a very general way, as Wen did, that this is realized if the ground state degeneracy depends on the topology of space. So if you have a system whose ground state degeneracy, for example, on the sphere, on the torus, or is different, then that's the definition of topological order. But more practically, what you would expect if you study the Hamiltonian, which are suspected to host this phase, is that what you should find is basically a degenerate manifold for the ground state, and then which is protected by a gap, and then the excitations are actually fractalized excitations, which are anyons, and these anyons can be either abelian or non-abelian, and there are actually many examples of that, like the KTF code or Z2 spin liquids, which have this feature. Now, yes.
So in the first definition, you have to compare degeneracies on many different manifolds to show topological order, right? I mean, I don't.
Honestly, I don't know. Yeah, don't.
The second one,
here.
You compute on torus.
Yeah.
But instead, you have to check the statistics of the excitation.
I think it's not a practical definition. I think if you really want to characterize your state, it's more looking at the ground state degeneracy on a. Yeah, and then you're trying to understand the property of the excitation, and which is going to be hard for us anyway. It's not what we are going to do, but.
Okay, just looking at the ground state degeneracy on torus, is it sufficient to say topological order?
I think yes, because then you know how to construct. I mean, if you know it's the same issue about knowing what are the anyons. No, so if you have the anyons, you can construct the different degenerate ground state.
Okay, but that argument already uses anyonic statistics, right?
Yeah,
so
right.
Okay.
But different types of topological order could have the same degeneracy, though.
Sure.
That's right. Yeah.
At least to say data topological order, I was kind of trying to ask what is the minimum information we have to get. Do we have to compare different manifolds?
Okay. It's not what I'm going to do anyway. Okay. So because we don't know how to do that, but the thing that we are really going to use and as a practical tool to characterize the topological state is by investigating the edge states, and that's really the thing that will help us to characterize the type of state, and so the thing is that if you have this topological color system, if you just imagine that you take like a sphere and you just cut the sphere into two hemispheres, then you expect to have gapless modes, Carrel gapless mode on the edge here, and these gapless modes are actually protected by the long-range entanglement, and they are very precise property. They are described by conformal field theories, and so they should have a very it's really a fingerprint of the type of phase. And so the technique we are going to use is very efficient to actually access the Carrel the Carrel edge states. So this is why I think it's a very powerful technique to identify such phases. So you will be able to judge by yourself whether it's convincing. So now there have been a number of microscopic models, in particular spin 1/2 microscopic model where Carrel spin liquid have been identified as ground state. So for example, as Alex told us yesterday, if you take this Heisenberg Hamiltonian on the Kagome lattice with this chiral term, which is which apply on every triangle, so it's a chiral triple product. Then it has been convincingly shown that for maybe a small critical value of this coupling, J chiral, there is actually a chiral spin liquid which is of this Kalmeier-Laughlin form, and that the edge modes are actually indeed described by a simple C=1, central charge 1 CFT, and the counting is exactly what is predicted by the SU2 level 1 Weizhou-Minot-Witten theory. So there are also other other examples. For example, on the triangle lattice, where such chiral spin liquid were found, and the nice thing is that in all these models you actually add a chiral perturbation. So these models, they break time reversal, but it turns out that you don't need to actually break time reversal in those models to all such phases. And there are examples like on the Kagome lattice with longer range frustrating interaction like J1, J2, J3, where the time reversal symmetry is spontaneously broken, and then the ground state is a chiral spin liquid. So actually, in this case, you have the two possible chiral spin liquid with which are complex conjugate wave functions. Okay, so what I will start with with actually not a Kagome lattice, but with a square lattice, and my initial motivation was to try to use tensor network to this. So I will take a very simple model on the square lattice. And this model actually was suggested in this paper. So what they do is they consider the Kalmeier-Laughlin state. And what they do is they basically rewrite the wave function as a CFT correlator of SU2 level 1 conformal fields. So I think that was explained in one of the talk by Steve Simons, how one can write this wave function in the following form. And the nice thing is that from this all this technology, they are able to derive an exact parent Hamiltonian. And the bad thing is that this parent Hamiltonian turned out to be long range. So it has like 3-side interaction at all possible distance with some amplitude that decay algebraically. So it's not a very good news. But in this paper, what they do something dramatic. They say, okay, let's forget about the long range part of the Hamiltonian, and let's just truncate, okay? And they end up with, they just keep the first term, that short distance term, and what they suggest is that this Hamiltonian, which include only nearest neighbor, next nearest neighbor, and this chiral plaquette term. So PIJKL is just a cyclic permutation on the plaquette. And this Hamiltonian will host the same Kalmeier-Laughlin phase, okay? But to do that, they have to do some fine-tuning of the parameter J1, J2, and they basically, from their paper, I tried to draw a schematic phase diagram where this Kalmeier-Laughlin phase should appear as a function of J2 over J1 and Landesi, the chiral amplitude over J1. And so I've been trying to investigate this model with the tensor network technique in particular for two particular points where they say that the overlap with the Kalmeier-Laughlin state is very large on small systems. The other interesting work along the same line is by Glasser and the same authors. We introduce a parent Hamiltonian for a non-abelian chiral spin liquid. So here what they do is they use the same framework, but where they start from the bosonic Murid Pfaffian state, which is here, which is supposed to host non-abelian anyons, which have the following fusion rules. So these are basically Ising anyons, which are non-abelian. And they use the same techniques. They write this wave function as a CFT correlator, but now it's a different CFT. It's SU2 level 2 CFT. And they end up with, again, an exact parent Hamiltonian. But now the difference is that it's a spin 1 model. It's not a spin 1/2, it's a spin 1 model. But again, it has long-range interaction. And they do the same thing. They basically say, OK, let's just truncate this model and just keep the short-range part of the model. And so they end up with this type of model, which I'm going to consider. So it's spin 1 on the square lattice with, it has, again, the J1 and J2 interaction. But in addition, it has biquadratic interaction on nearest neighbor and next nearest neighbor sites. And it has the chiral term, the previous chiral term, but which now is written for spin 1.
Is there an exact reason for why you have a spin 1 instead of spin 1?
Well, I think one argument is that if you want the edge state to be described by SU2 level 2, then probably you need spin 1. Yeah. Yes. Oh, no, yeah, right. But I think the question is, why can't you just host a Mouride state in a spin 1/2 model, which would not have the biquadratic? But I think it's because of you want to set up something which would have spin 1 edge modes, which are known to in some fine-tuned Hamiltonian, which are described by SU2. Yeah, exactly.
If you show the Pfaffian state wave function on the previous slide?
Yes. So Q here is, in this case, so it's not the usual fermion Pfaffian. Here it's bosonic, so you have to take, it's not Q equal 2, here it's Q equal 1, and it's a filling factor nu equal 1 instead of 1/2 for fermions. So the one that was, lot investigated was nu equal 1/2 fermionic for the half-filled second Landau level. But this one is a bosonic version. Yeah. Well, in their paper, they also studied the fermionic one, but the one which has this nice SU2 symmetric parent Hamiltonian is a bosonic Mouride state. OK, so that's basically the goal. So let's investigate these models, and let's see what we can do with the technique I will describe. So to explain the technique, I will start with something very simple. So how can you write a topological liquid in terms of tensor network? So I will start with the spin 1/2 RVB state. So with this state, as you know very well, is the equal weight superposition of nearest neighbor singlet coverings. And actually, since there is one spin 1/2 on every site, it fulfills the Lipschutz-Matisse Hastings-Oshikawa theorem. And it has to be either gap topological spin liquid or critical spin liquid, and actually depends on the lattice. So on the square lattice, it would be critical. Now, this state, the nice thing is that this state can be written as a particular kind of tensor network. And the construction is very simple. Actually, the construction is very similar to the Affleck-Kennedy-Lip-Tasaki construction, the AKLT state. So what you do is basically on every side of your lattice, you attach virtual degrees of freedom. So these virtual degrees of freedom are the red sides. And these virtual degrees of freedom are either spin 1/2, plus or minus spin up or spin down, or they are singlet. So this is what this plus means. This is the reunion of these Hilbert spaces on the virtual sides. And what you do is basically, so since you have on every side, you can make maximally entangled pairs between these virtual degrees of freedom between the site on the links of your lattice. So this is what this green thing means. They are just maximally entangled pairs. So this is a singlet, and this is just 2 spin 0 on each side. And then you get something which is not entangled. It's just a product of these maximally entangled pairs. And to construct the wave function, what you will do then on every side, you will act with a projector map on the physical space. So for example, you will take these 4 virtual spins here, and you will project, for example, on the spin 1/2, which is the physical space. And if you do that, you get exactly the RVB state. And the reason is that when you do this projection, you can either, either take a spin 1/2 here, or here, or here, or here, and the rest are 3 spin 0. And so that reconstruct the linear superposition of all these valence bond pairs. So this is an exact way of rewriting the state. And then this projection thing you can actually write as a tensor. So on every side of your lattice, you will have a tensor, which has virtual indices here corresponding to these degrees of freedom here. So these are these alpha, beta. And you have some index R here, which is a physical spin, which here is up or down. And so it's a very simple thing. So you can rewrite your wave function, you can rewrite your wave function in terms of just one tensor. So in terms of a small number of parameters. Yes, Carlo.
This is the Roxanne-Stevenson point wave function?
No, this is the SU2. It's not a dimer. It's not a dimer wave function. It's really the SU2 version of the Roxanne-Stevenson. So it's really the RVB. For the Roxanne-Stevenson, you would just need, like a particle here, featureless particle, and a spin 0. And
But
you would not need the spin 1/2 here. Here you really have up and down to construct the singlet.
Orthogonality of different singlet orbits.
They are not orthogonal, yes.
In that sense, it's not
Right.
but it's the equivalent.
Actually, we can construct a more general tensor network that interpolate between the Roxanne-Stevenson, where all the valence bond configuration are orthogonal to the RVB. So there is a continuous path that we can construct.
Yeah. Question. Why you cannot have 3 singlets?
Yeah, so that's a good point. So actually, you can extend the wave function, and I will show. Yeah, so if you want to reproduce exactly the RVB, you have to say that all the tensor elements where you have 3 spin 1/2 are 0. But you can consider more general, and actually I will use it more general ansatz where you have actually 3 spin 1/2 and 1 spin 0, and this you can add to the other one, and so you get a family of extended RVB state. And that would correspond to RVB state, which has longer range bonds. And actually, on the square lattice, you can show that there would be a transition from a U1 spin liquid to a Z2 spin liquid as a function of this parameter. Okay, so now how do we do? So what we do is basically we take, so it's, for example, you can construct a wave function on a cylinder by putting these tensors on every side of the cylinder. And now the weight of your wave function, so this is your local basis here. The weight of your wave function is described by just contracting this product of tensors. So it means I have to sum over these virtual indices. They are not shown here, but they are on the links here. And you have to sum over all possibilities, all configuration of virtual indices. This is what we mean by contracting the tensor network. And this tensor network, they are called projected entangled pair state. So it's a class of tensor network. So do you have any question about the construction, or? Okay, so the thing to remember is that basically I have a complicated wave function with exponential number of coefficients here, exponential scaling of the weights, and this is just represented by this very simple object, this side object, which is a tensor, and which doesn't scale. The Mer parameter doesn't scale with system size; it's just fixed. And the key parameter is actually the dimension of the auxiliary space, this capital D. And this capital D, which is the number of virtual degrees of freedom, is what is controlling the entanglement in the wave function. So if I want to construct a very much entangled state, I have to try to get as many virtual degrees of freedom as possible. Okay. So now let's come back to the question of the chiral spin liquid. So I want to use this technique to design some ansatz which are chiral. And so there is a minimal requirement. Well, it's a sufficient requirement. Maybe it's not necessary, but it's sufficient, which is the following. So assume now I want to only use one tensor on every side for simplicity. What I'm going to require is that if I look at the point group operation, like the mirror symmetry around the site, I want to require that my under all these mirror symmetry, my wave function, my ansatz, will transform into its complex conjugate. So it's a time reverse partner. So in this way, I will have a wave function that breaks time reversal symmetry and parity, but it will not break the product PT, okay? Because parity is same as time reversal. And the way to do that is to actually write a tensor network which will give two parts of the wave function. One part which will be fully symmetric, and one part which would have what I call G symmetry, that is, which is odd under any reflection. And the nice thing is that the tensor network, all these, this is a global property of the wave function, but in the tensor network formalism, I can implement this property locally at the level of the tensor. So if I write the tensor as A1 plus IA2, where A1 is a fully symmetric tensor and A2 is, let's say, antisymmetric tensor with respect to mirror symmetry, then I know that my global wave function will have the same property. So this is, I think, a very powerful thing that enables to construct this chiral spin liquid wave function. So, yes?
Excuse me? Say again what the symmetry of the S part?
So the S part is like, well, here, I'm using notation of atomic physics for orbitals, which I'm not completely allowed for a discrete group, but S is like S wave. It has all symmetry and the reflection, rotation, everything on the lattice. So in terms of the irrep of the lattice point group, which is C4V, I mean, this guy is like A1 representation.
Very naively, it looks like this part is not odd under doesn't transform into its complex conjugate under
this one? It does, because this one is, no, but you want complex conjugate. So you want the real part to be invariant, and you want the imaginary part to pick up. Sorry. So psi, these things are real. And the complex and the imaginary part comes only with this I factor. Yeah. So this guy is invariant under mirror symmetry, and this one picks up a minus sign. So the global wave function is get into its time reversed. Okay. So now to come back to Federico's remark, I can actually extend my RVB PEPS. And the construction is exactly this. Before, on the 4 virtual sites, I had only 1 spin 1/2. But I can also construct tensors where I project 3 spin 1/2 on a spin 1/2. Okay, and you can actually show that there are only 2 ways to do that. One way is by with a S-wave type of projector. And another way, which G-wave, exactly a G-wave projector, which so it means that the wave function by projecting 3 spin 1/2 to a spin 1/2 would have exactly the G-wave symmetry. It would be odd under mirror symmetry. And so it means that with this virtual space 1/2 plus 0, I can construct this tensor. So I will take this tensor is just the nearest neighbor RVB. This one is the tensor that describes longer range bonds of S-wave symmetry. And this one here is the other one, but which has G-wave symmetry. And I put this I lambda chiral. And now I have basically a family of tensors that give me a chiral spin liquid. And actually, you can show that this is the simplest representation of the abelian chiral spin liquid. So what I want to do now is I will show that we can generalize this construction to any possible virtual space here. But before I do so, what I should discuss is the fact that there might be some obstruction. And people in the field have discussed whether there was some doubt that it's possible to construct really a chiral spin liquid with PEPS, in the sense that I want a state which has short range correlation and all the right properties. And the doubt comes from an exact proof by Dubai and Reed, but for the case of non-interacting PEPs, so which are called Gaussian PEPs, which describe actually free fermions. So it's not a general proof for interacting wave function, it's just for non-interacting free fermion wave function. And the theorem tells that actually these chiral tensor network have no gapped local parent Hamiltonians. Okay, so reversely, if I have an Hamiltonian which I expect to have a gapped spectrum, then I cannot describe it with this tensor network ansatz. And it is basically exact. So there have been some work here of these Gaussian PEPs, and these people try to find parent Hamiltonian, and they basically find two classes of parent Hamiltonian. Parent Hamiltonian which are either the one which are local, which have local interaction, but they turn out to be gapless. And if you relax the fact that you want your parent Hamiltonian to be local, but you allow for long-range interaction, then they can be gapped. But you have to put long-range interaction. And so, yes?
So what does it mean, like free fermions?
Well, these are a special class of PEPs, which are these Gaussian PEPs, which I never worked on, but that describe non-interacting particles.
So it's like a construction to construct a virtual space.
Yes.
In some way.
Yes. Yes. Yes.
Fermions,
Exactly.
And then still you project somehow.
Yes. Yes.
Okay.
I've never really worked at them, but the idea is that they describe non-interacting particles. That's the key thing.
So split of the two.
Yes. Yeah.
So project to the space of the two.
Yes. I think so. I've never.
Yeah, the same question was asked to Antoine Sterdignac.
Yes. What did he say?
His answer was that this free fermions state obey Wick theorem. Kind of Gaussian.
Yeah. Okay, but morally, what you have to remember that they describe free fermions, basically. So you cannot use them to describe anything correlated.
But in terms of if you want to write them as really using tensors, they have infinite bond dimensions, I guess.
Probably, yes. Yeah, the virtual space, you mean? Yeah. Okay, so now the concern is that for if you want to use really a PEPs to describe interacting spins, is there any obstruction to construct what we really want to see, which are these gapped chiral topological PEPs? And so far we don't have any example of such PEPs. Like in this paper, they have a chiral topological PEPs, but the states were showing diverging correlation lengths. So is that a generic feature that you, when you try to reproduce the physics of your Hamiltonian, which might host this short-range chiral spin liquid, is that a generic feature that you actually always get some ansatz which has long-range correlations? Okay, so this is what we want to see, and trying to study more example, and maybe we can learn, from this example whether it's generic or not, and if it's generic, why is that still reliable to do so? And what is the form of these actually long-range correlation part that you have to have in your PEPS. So to go beyond the simple example I showed, this RVB, this chiral RVB state, one needs to do a more systematic construction of these PEPS. And so what we've been doing is trying to implement some general construction using classification of these SU2 invariant PEPS. And the idea is basically, since you remember, I need to use the point group symmetry to construct the real part and the imagined part of the tensor. So what we want to have, in addition to SU2 symmetry, we want to use actually the point group symmetry of the lattice. So we want to do a classification of all these tensors according to the point group symmetry of the lattice. And the idea being that now can construct the tensor as a real part, imaginary part, and these two guys, they will belong to different EREP. So this one will belong to the, let's say, A1 EREP, which is the one which is fully symmetric, and this one will belong to the A2 EREP, which is the one that gets a minus sign when I do a mirror symmetry. And so here I list some example for spin 1/2 and spin 1. So what is here is some possibility for the virtual space. So it always comes as a direct sum of SU2 EREP. For example, spin 1/2 plus spin 1/2 plus spin 0. So that will give a bond dimension of 5. And then you can show when you do this systematic classification that there will be 10 tensors of the A1 kind and 8 tensors of the A2 kind. So here this sum will contain 10 terms and what did I say? 8 here. And then I would have some coefficients. So this tensor will be fixed. Okay, we have even analytical expression for these tensors. And this guy here will be some parameters, some real parameters. I am allowed to tune to reduce the variational energy. So that will give me a variational, family of variational ansatz. So for spin 1, for example, this is the same thing. So if I take this representation, for example, 1 plus 1/2 plus 0, so this is so it means on the visual level, I will have, spin 1 degrees of freedom, spin 1/2 degrees of freedom, singlet degrees of freedom. And then you can see in this table that I will have 13 of these tensors here exactly, and there will be 8 here on this side. And I have 21 parameters to tune. So it's a very small number actually. It's much smaller than the tensor element, because so that allows actually to do brute force optimization. I can really optimize. I don't have to do any imaginary time propagation or anything like that. I can really do brute force optimization of the tensors. So how do I do that? So I will use the iPEPS method. So it means what I want to do is, yes, Carlo?
You have an energy optimized the energy,
Yeah.
optimize your correlation function.
I optimize the energy. I have so this is what I'm going to explain how to compute the energy. So for each choice of the parameters, I can compute the energy, and then I will just feed some conjugate gradient routine to do a brute force optimization with respect to the parameters. And it works very well, but this is possible only because we put the symmetry, and the number of degrees of freedom actually is not growing very fast with the bond dimension. And this we will do, we'll compute the energy in the thermodynamic limit from the start. So we assume that we have an infinite system. So we have our tensor network on the infinite system. And then what we do is we use some real space renormalization scheme, which is called the Corner transform matrix renormalization scheme that was actually used for classical StatMech problem in the past, introduced by Nishino and Okunishi and others. And the idea is basically very simple. You start from infinity, and then you add sides one by one. And what you want to do is so this is, assume this is your corner transform matrix. so that's your environment. That's at step n. Okay. Then you add one site, and then this you do some kind of SVD or excitonization, and you basically throw the entanglement that you cannot keep. Okay, so at every step you add one site, you increase the entanglement, and then you do SVD, and you keep the relevant degrees of freedom to keep the dimension under control. And this is how it works. So the nice thing is that you can keep.
Sorry, do you put symmetries in the corner?
Yeah, exactly. So the thing is that we, since we have the symmetry in the tensor, where we can actually keep the SU2 symmetry and also the point group symmetry. So at the end of the day, what we want at the end of the day is to build an environment around some active object. So this is where we apply the Hamiltonian, let's say on the plaquette. So because of the symmetry, we know that all these corners will be the same. Okay, and all these environment tensors here on the edge will be the same. So we only need to compute, to do the renormalization at one corner. And so also what we have is that we have reflection symmetry here with respect to all possible mirror symmetry. And the SU2 symmetry is also kept. Exactly, yeah. So we mean when we do the truncation, we have to keep, we're not supposed to cut within SU2 multiplates. We have to keep all, complete SU2 multiplates in the renormalization scheme. Okay, maybe I should speed up a little bit. Okay, so this is basically the technique, and let me show you. So there is one parameter, one key parameter, which is our approximation parameter, which is the environment dimension. Okay, so it's another parameter. It's not capital D, but this is the blue line. They are actually they have dimension chi, and this is what is controlling the CTMRG procedure. And of course, if we want to do the construction as exact as possible, then we have to take key, as large as possible. So what we are going to do is we are trying to do an approximation for chi going to infinity. And so this is what I do here. So this is the energy for the spin 1/2 and the spin 1 models. So this is basically the same time of plot. So let's concentrate on this one for the spin 1. So what is plotted here is 1/chi in unit of d square. And the nice thing is that the energy per side, the energy density, is actually converging systematically, like linearly with 1/chi. So you can do really a nice 1/chi going to infinity extrapolation, and these correspond to different ansatz, so which are listed here. And for example, the best energy we get is for this particular ansatz, which contains spin 1, spin 1/2, and spin 0. It's just a simple d equals 6 PEPS. And this is a comparison with DMRG. So these are DMRG extrapolation on cylinders. And you see that the energy is very close.
So for the given virtual dimension, you
Yeah.
need to extrapolate.
Exactly. We did not attempt to extrapolate the extrapolation. No, you could extrapolate in chi and then attempt to extrapolate with d, but that's okay. This we haven't tried. But already for finite d, this is what this tell you, that even for such a small bond dimension, the energy is very good compared to the MRG. And the thing is that we have an ansatz which has the complete symmetry of the problem, which is very nice if you want to compute the, let's say, the edge state. So which is what I'm going to do. So what I want to investigate. So remember, I want to characterize these chiral spin liquid are characterized by chiral edge modes. And so I want to identify the nature of these chiral spin liquid from these edge modes. And so what we are going to use is something that was proposed by Lee and Haldane, which is actually the edge mode spectrum is actually contained in the entanglement spectrum. And so what I'm going to do here, I'm going to compute the entanglement spectrum on a cylinder. So I have a very long cylinder, let's say infinite cylinder, but it has a finite circumference. And what I'm going to do is I want to compute the entanglement spectrum. So I have to compute the reduced density matrix of the left side, for example, of the half cylinder. And the entanglement spectrum is defined by rewriting this positive operator in terms of exponential of minus some Hamiltonian. And the spectrum of the Hamiltonian will contain the H-mode spectrum. Now, it's not clearly obvious because the support of this operator is really the physical space on the left. And now, the nice thing about the IPEPS framework is that there is a bulk edge correspondent that relates the reduced density matrix on the A side to some operator that actually lives on the edge exactly. So there is a correspondence between this guy and some operator sigma b square, which is a positive operator, that actually acts on the edge degrees of freedom. It's no longer acting on the physical degree of freedom, it's acting, so it's really a one-dimensional operator on the edge. And this is rigorous, this identity is rigorous, and U is basically an isometry that conserves the spectrum. And we know how to construct the sigma b square operator, which is a nice thing. It can be obtained from the fixed point of the transfer matrix here. And so now sigma b you can rewrite also as exponential of minus some operator, and now this operator is really acting on the edge. So this operator in the spin 1 case would be an operator which is acting on a chain that contains on every side, it contains spin 1, spin 1/2, and spin 0 degrees of freedom. So the Hilbert space of the chain is 1 plus 1/2 plus 0. And so what we want to do is to compare the spectrum of this guy here to the prediction of the chiral CFT that is supposed to be realized. And so I show you the result for the spin 1/2. So what should we see? If in the case of the Camille-Laughlin-like state, we should see chiral Luttinger liquid described by the SU2 level 1 theory. And so it means that we should really see a conformal tower of states with very precise content. So we should see some chiral modes. So linear dispersing modes in only one direction, let's say right moving modes. And for every momentum, there is a specific content. There is a precise multiplet content. And this is what is listed here. So the first, that would be the state at momentum 0, that corresponds to a singlet. And then at momentum, let's say 2 pi over L, where L is the circumference, there would be a spin 1. So I don't know why they put 2 here in this CFT book. I mean, this is really a spin 1 here. Here is a spin 1 plus a spin 0, next level, and so on. So you can really, for every level, there is a precise content. And so for the SU2 level 2, I didn't find in the yellow book, so I asked actually Benoit to help me to to construct the conformal tower. And this is also the content that we should see. So first level spin 0. So actually there are 3 sectors that we should see. And so here spin 0, spin 1, spin 0 plus spin 1 plus spin 2, and so on. And then there is another sector corresponding to odd half integer spins. And there is a third sector which actually I don't know yet how to construct. But these 2 sectors, topological sector, I know how to do it. So now let's see what our numerics tell us. So this is the entanglement spectrum for the spin 1/2 Hamiltonian. And what we clearly see is linear dispersing chiral modes here. So this K is the momentum along the edge in the transverse direction.
So that's after optimization for some Hamiltonian.
That's right. This is for the yes.
The Hamiltonian.
Oh, the Hamiltonian is the one for which we get the best energy before. I have a different choice of the tensors. Oh, what is the Hamiltonian? Oh, the Hamiltonian is what I showed at the very, very beginning. You remember? I mean, it has a spin. It has a J1 nearest neighbor, J2 next nearest neighbor, and it has a chiral term. And this is for a particular point in the phase diagram where it's supposed to be to have the largest overlap with the Casimir-Laughlin. And the other one is the fine-tune, also fine-tune. The spin one is more complicated, J1, J2, K1, K2, and the chiral, and with fine-tune parameters. Yeah, so you see, so there is a subtlety that actually Antoine told you maybe last week that they have resolved. The subtlety here is that because of some, symmetry interplay, the momentum here is only defined modulus pi. And the reason is that if you want to have, implement all the tensors, the fact that you have only one tensor per side and that the tensors have the full point group symmetry, then you have to, then the generator of the SU2 group are not invariant under translation by odd number of sides. They are invariant by translation of 2 lattice spacing. And so it means that the momentum is defined modulus pi, and so this branch actually, it's like the chiral mode is folded in the reduced Brillouin zone. But they found a way, which is quite simple, to basically unfold the spectrum. So you should not be worried that actually everything is folded in the reduced Brillouin zone. There is a way of unfolding the spectrum. So that has a real expected form. And then what you can read here is really the content of all these level, and this, what is written here, is exactly what is predicted by the CFT. So this, for example, here there are one quintuplet, there are 2 triplets here, hidden here, and there are 2 singlets here and here. Okay, and you can really look at all the levels. It works very well. Yes.
So what you're showing, this is the property of your wave function of your tensor network.
Yes.
With the 20-something parameters.
Yes. Yes.
How, and you optimize the parameters for the
Sure.
Hamiltonian, but you can take random parameters and check what is the entanglement spectrum.
Yes.
How much?
No, but we have big, high-dimensional families, so we cannot, explore the whole family space.
How much is a generic feature of those, of that type of tensor?
I don't know. It's like you asked me the question, how generic is the parent Hamiltonian? I mean, this parent Hamiltonian is also fine-tuned, to get the largest overlap. So I really don't know. I suspect that if the state is if you describe a gapped spin liquid, then there is some. It is robust against small deformation. So there will be some area in the parameter space in the family of PEPS where everything remains is generic, but I don't know how large is. But for sure, it's really a fine-tuned PEPS in the sense that it is optimized for the particular Hamiltonian that we have. Yes. Yes.
Is the state supposed to be degenerate? The one in
Yeah. So it's like in Steve talk, no? I mean, in the CFT, perfect CFT, everything is degenerate, but here it's here we are on a finite ring. And so I suspect that's why we have some dispersion of the states. It's also an approximate.
You don't have problems with confinement potential?
No. The state. Yeah, that's right. But I have a finite ring, so I have finite size effect. No, So I suspect if I increase the size of the ring, everything will just go down, and all the K point will collapse, and then when I get to zero energy, everything will get narrower and narrower. Now, how it goes for the more exotic spin 1 case, and this is what we get. So these are unpublished data. So this is the 2 sectors we're able to look at. And again, you see these very nice linear dispersing modes, and the content, that the number of multiplets is exactly what is expected from for the chiral CFT, SU2 level 2 CFT. Even you can even go to to the 1, 2, 3, 4, 5, 6. You know, the 6th level is almost correct. I mean, this blue, when it's blue, it means there are some levels missing, which are higher up, but it's only a few levels. So even up to the 6th level, we get the right CFT content, which I think is pretty good. So it looks like we have a very good representation of this non-abelian chiral spin liquid. Now, what about the property of the bulk? And this is where it becomes more controversial. So the bulk. So how is the bulk? Is the bulk really with short-range correlation? Is that really incompressible state? Now the thing is, we can compute the maximal correlation length by using the transfer matrix. So remember, we have this tensor here that describes the environment. So when you contract everything up to a given, from infinity to a given to a given position, and from this, we can, from the diagonalizing this transfer matrix, it's like in StatMech, we can compute the from this spectrum here. And on the end, we can compute the correlation lengths, the distribution of correlation lengths in the problem. And what we find is that the correlation lengths, if you plot, this is a log-log plot, straight line. So they basically seem to diverge as a power law in chi. Okay, so this is for our d equals 6. This thing is for spin 1, d equals 6 PEPS, the best tensor that we have. So that would suggest that actually the bulk is critical. Now, is that really a severe deviation from what we expect? And I'm trying to convince you that it's not a severe deviation, it's just an artifact that should disappear when the bond dimension increases. So what is the argument? So now we don't know what operators show this correlation length. So what we did is we explicitly compute the correlation function. For example, the spin-spin correlation function with the following setup. So what we do is construct very long strips, and they are built from the environment tensors, on the side, and then here we insert the spin operator at some position as far as possible, and you can compute the correlation as a function of distance, it's a function of separation d. And this is what is shown here. So this is correlation function in log. This is semi-log. And what you see is that you see exponential decay, which is with some correlation lengths. And this is this correlation length, which actually diverges when I increase chi. Okay, so this is for a given chi. It has to be exponential, but this correlation length that I extract here is the one that actually is diverging when I increase chi. Okay, this is for a particular chi. You see, if I go back to the previous plot, what I'm doing here, I'm just sitting at a value of this parameter chi, okay, which control the CTMRG procedure, and I extract some correlation lengths, some correlation lengths here, okay, and for which is so it means that the correlation function decays exponentially, but this correlation length will diverge eventually if I increase chi. Okay. Okay. Now, so what it means is if I have, if I can go to larger and larger chi, then my correlation function will be a sum of exponential, and then there will be a continuous density of correlation lengths when chi becoming very, very large. And I want to see what would be the to which correlation function it will converge. It will eventually converge when I increase the number of correlation lengths. Right? So when chi going to infinity, there is a continuous distribution of correlation lengths, which is not bounded. The maximum one will just diverge. Okay. So the problem just end up to compute the the Laplace transform of this weight W of psi. Okay. At the end of the day, what I would have to do is to compute this guy. Continuous sum of exponential with some weight here. Okay. And this weight I can actually extract. So this is what is shown here. So this is a weight I have here as a function of the correlation. And this is a semi-log, and what it shows is that there are straight lines. So it means that this weight is decreasing exponentially fast with the correlation length when I tune chi. Okay, so at the end of the day, what I have is, I have this, expect to have this formula, and if I do this ansatz, I use the fact that this guy goes as an exponential. I plug it in here, and then I just do you can just estimate this by saying that what is in the exponential is basically doesn't vary, and what you get is this very nice form. It's just a stretch exponential tail. And this WD here, this depends on D, okay? And this is a weight of this stretch exponential. Okay? And this weight actually is very small. This is what you would get here by taking the intersect of these lines. You see the scale here, it's 10 to the minus 2, 10 to the minus 3. So it means the long-range tail has a very small weight. And besides, there's another information is that the weight seems to decrease very strongly with when you increase the bond dimension. So for example, here, this is for d equals 5 ansatz, and here this is d equals 6 ansatz. And there are actually 2 orders of magnitude of the weight when I increase d just by 1. Okay, so this weight WD of this, what I claim is a stretch exponential tail, seem to decrease very fast with d. Okay, so what we have is basically at the end, just to summarize, at the end of the day, what do I have? I have some correlation function which is some short range part, which is very short range decay, and that's consistent with the either the Camille-Laughlin state or the Murid state. I expect really a short range decay, and then I have a tail which has a very, very small weight, and this weight is actually decreasing very fast. The weight of the tail is decreasing very fast when I increase the bond dimension. So I think this is a way to reconcile, the study with the no-go theorem. That is, you need to have to get these. There is an obstruction. We mean that I cannot, strictly speaking, for finite d, construct a chiral spin liquid which is short range, strictly speaking. But what I have is just some artifact, some long-range tail, whose weight is very small and which will eventually disappear very quickly when I increase the bond dimension. So I think at the practical level, it's not a practical obstruction in a way, just conceptual thing. Okay, so I don't know whether you buy that, but this is my understanding.
So you mean
at the
that
moment.
the bulk is gapped finally? You think your results are not inconsistent with that?
Exactly. I think that the state will not. There would be two scenarios. One scenario is that the Hamiltonian they produce is so much different from the parent Hamiltonian that it will be in a different phase, and the phase will be critical, and the PEPS will give the right physics. But the other scenario, which now I believe is probably more the truth, is that the Hamiltonian really hosts these gapped chiral spin liquid phases, as it was suggested in the paper. But now if you investigate with PEPS, what you get is some approximate form of this chiral spin liquid, in the sense that the wave function have this this artifact, this long-range tail, but of a very, very small weight. So practically, it's very similar to short-range correlation up to this very small tail. And this is why the energy is so good, actually.
Still, at finite d, if you take chi to infinity, at the end you have a power law for spin.
No, that's the point. The point is the power law. To get a power law, you need to take the Laplace transform of a power law. And what I'm saying that the weights are not power law, the weights are exponential. So at the end of the day, that's exactly the point. So the C of D here is not a power law. Well, it could be a power law with a weight which goes to 0 very fast, but I think it's even better than that. It's actually a stretch exponential which decay faster than any power law, but whose distribution, if you write, is the distribution of exponential. It has, it is not bounded. This W of is not bounded. It has weight for all, correlation lengths, but this weight decay exponentially fast. So if you plug it in here, you get this distribution, this correlation, this tail.
Can you go back to the plot of the
Yes.
correlation themselves?
Yeah. Yeah. So the thing is that for a given chi, okay, I'm trying to obtain the form of the what the real information we have is just this one. It's really we have a discrete sum of exponential, and so what I'm trying to do is I'm trying to guess what will be the limiting correlation function by summing all these exponential, and the argument is that for large d, for large separation, this omega here of chi, which I can actually compute and plot, is actually going exponentially fast to 0 with some new length scale, lambda d. And so because of these weights are going very quickly to 0 as an exponential, then the power law, the limiting power law for when chi go to infinity is not the limiting correlation function is not a power law, but is something that decays faster than any power law, but still is decay less rapidly than a single exponential. So it's in between. I think if you want really to get a power law by summing this exponential, you need this weight here W to decay much less rapidly as we find here. So that's my guess. So it's not dramatic. It's just something that decays more rapidly than any power law, but it's not an exponential. So conceptually it's long range, but not as long range as a power law. Okay. It's very speculative, I admit, but this is the best we can get so far from the data. Okay, so maybe I should conclude. I think that these chiral PEPs, they offer both, a quantitative understanding because we get, very good ansatz in terms of energy, for example, but also conceptual understanding of the spin 1/2 and spin 1 quantum antiferromagnets, which were proposed to host these gap topological chiral spin liquid, which are the spin analogs of the fractional quantum Hall states. So one speculative result that we suggest, that the data suggest, is that there is actually what I call a Gauss-Hammer long-range tail in the correlation function, and that's in agreement with somehow with the no-go theorem. But I think it's not an obstruction to describe in a very accurate way the gapped chiral spin liquid with PEPs, in a way. And the other thing that we've seen is that the virtual degrees of freedom that we introduce when we construct the PEPs actually play a physical role at the boundary, because these are these degrees of freedom that actually correspond to the from which the chiral edge modes are built. And the outlook is to look at other lattices, like the Kagome lattice, and other symmetries like SU3, SU4, and so on. And last, I would like to thank my collaborators over the years in this project. So the initial design of chiral spin liquid, Ignacio Chirac, Norbert Schur, Jan Affleck also we contributed at some point. The classification that I shown was mainly done by Mathieu Mambrini in collaboration with Roman Horus. And then we moved to the investigation of these chiral antiferromagnet with Mathieu again, and more recently the spin 1 has been done by my postdoc, Ji-Yao Chen, and in collaboration with Sylvain Caponi and Lawrence van der Streeten. Okay, thank you very much.
Can you get an extrapolation from the state, since the conclusion is that it should be gapped?
Yeah, I think the short-range physics is something which is very robust, that we pick up even for small bond dimension. So this is what I showed. You know, if you look at the short-range correlation, this is something that is basically converged.
So this is
It's not the gap. It's the short-range correlation length, which is very short. So if you look at this plot, this is what I call psi short. This is 0.6. It's less than one lattice spacing.
But this is the quantity that you would relate to the gap.
Exactly, exactly. So this is the thing which is not, which is robust, which is not an artifact of the PEPS construction. And actually, the short-range correlation is not varies very little with the bond dimension and with chi. Yeah.
Maybe I just missed your explanation, but in the entanglement part, you showed us an entanglement spectrum corresponding to different topological sectors.
Yes.
So, but normally, different topological sectors correspond to threading different topological fluxes on the cylinder.
Yeah.
So how is it possible to implement topological flux threading?
Yes. Well, this is what I do. I put under the carpet, but the way we construct these topological sectors is by playing with the boundary condition. So there is actually a gauge symmetry in the PEPS, which I haven't described, which is why actually you can. You know, the nice thing is that the gauge symmetry is related to topological order, and the gauge symmetry here is Z2 gauge symmetry. So this is why you can construct actually the even and odd sectors by playing with the boundary of the. You know, it's like playing with the boundary of your cylinder, and that give you the even and odd sector that I showed, corresponding to the j equals 0 and j equal 1/2 sectors of the. But now there should be two other ones, as you mentioned, which is by playing with putting some kind of Z2, you know, Vison line along the cylinder. No? And this is more complicated because now I have this chi degree of freedom in the transverse direction, and if I would put a Vison, then I have to define what is the operator in this new degree of freedom, which are the Vison operator. So in principle, I could construct 2 by 2 4 sectors, and among these 4 sectors, there should be the 3 sectors that we are expecting. So I can only get 2 because I'm not playing with the Vison lines.
So I think that's for Z2 spin liquid. So what about the monoid spin liquid, chiral spin liquid correspond to monoid state?
Yes.
So you have 3 different.
Exactly. So we have 4 total. We can construct 4, but among the 4, some are they are not 4 linearly independent. So I think among the 4, there should be only 3 linearly independent. So I have 2, which are obviously linearly independent because they correspond to even and odd integer and half integer spins. But I have another sector corresponding to the j equal 1, topological sector, which are integer spins, and this one I think I can construct with these Vison lines, but it's more complicated, and since I'm lazy, I haven't done it. Basically.
Maybe I didn't quite follow. So in the beginning, you introduced this noble theorem.
Yes.
So that applies as a mathematical theorem, also applies to your
It doesn't apply to that. It applies only to Gaussian PEPs, which are, where we discuss is non-interacting thing. But it gives a strong suspicion that for interacting PEPs, it will also apply. But I think there is no exact proof in this case.
For in the original version of that theorem, which applies only to some other kind of PEPs.
Yes.
But what is the exact statement?
The exact statement is that these Gaussian PEPs, they cannot have parent Hamiltonian, which are both local and gapped.
Oh, it's a statement about parent.
Yes, I think so. Okay, I think this is what it is, but yeah.
So you somehow construct your PEPs as being like spin singlet and transforming on the time reversal symmetry and like odd.
Yes.
But so is it like that every state that transforms in this way is like topological?
No, no, I don't think so. So this is
But
why.
also if it's a singlet?
No, it is a singlet that by construction. It has the right property, but I think you need some gauge invariance at the PEPS level to be able to write to construct a topological state. So this construction is not guaranteed that you get something topological at the end of the day, just because of this construction. But if you have a gauge symmetry, then you can expect maybe you get something topological. But it's not guaranteed. Yeah. No?
Starting from your PEPS, can you construct those non-abelian ions somehow?
Yeah, that would be very interesting. Yeah, yeah. You have to think how we can. In principle, yes. If you have the gauge symmetry, then in principle we can introduce some, some lines, some like, and try to construct, localize, at least localize anion by applying these lines of operators on the bonds. Yeah. Conceptually it's possible, but now practically, I'm not sure we can really test, the fusion rules and this type of thing. Conceptually, yes, we can construct localized anion. If we have the, the Wison operators on the bonds, we can do that, and it's associated to this gauge symmetry of the tensor.
No other questions? Okay.
Thank you.